Everyone. Hope your day is going well. So this is Volcanoes Lab 3, or Lab 7 overall, so you're over halfway. So that's pretty exciting. So a big element of this lab is mental convection, which looking at the mantle here, the mantle has some parts that are kind of liquidy and then some parts that are more solid, and it depends how deep you are. It's kind of a gradient. And just depending on that temperature difference, it'll circulate. So we have this circulation going on all throughout the earth, which if you look at like a boiling pot of water, we kind of see this as well. There's like a circulation to it. And it will create these upwelling zones where with this warmer material upwelling. And we see this at mid-ocean ridges. So if we remember from the earthquakes lab back a few weeks ago, these mid-ocean ridges are where a new volcanic crust is formed. And so it'll form this volcanic crust and separate apart. And then over time, it will subduct at these subduction zones certain ways away. So these mid-ocean ridges form at what is called divergent plate boundaries. This should all hopefully be review. Divergent plate boundaries are when the plates kind of move apart there. And then this is happening due to a process called decompression melting, which that upwelled material, that hot material coming up from the mantle, will melt these rocks, creating these magma chambers, allowing for new crust to be formed. And so now looking a ways away at these subduction zones, when this oceanic crust subducts underneath this more buoyant continental crust, it will melt down in the earth because we're getting deeper and it'll get hotter. And then it's also melting due to a process where water will get mixed in with the rocks. Since we're subducting from the ocean here, water will get mixed in here as well. And when we have water mixed in, it will change the chemistry up a little bit, and it will allow these rocks to melt a lot sooner in a process called partial melting, which will make magma. And this magma will create volcanic chains. And then this is kind of getting out of my element a little bit, but I think it partially melts because the water, when it gets trapped, normally it would just evaporate away, but since it's trapped underneath the ground, it just gets really, really hot and it has nowhere to go, and water holds its temperature really well. So that just mixture just makes things really hot to the point where it can melt rocks. So this lab's going to be looking at different heat flow and freezing point depression problems. So a big concept is that heat will flow to cold areas. So if you heat your house, the heat's not going to just stay there. It's going to flow to the outside where it's cold. And then melting objects will absorb heat. So if you have an ice cube, it's absorbing heat in order to try to melt down to a liquid. And then this is a concept called heat of fusion, where the amount of heat needed to melt it. Heat of fusion is the amount of heat needed to melt a measured mass of an object. And then this is a little backwards to think about, but freezing objects will actually release heat because it takes a certain amount of energy to melt something down, and that process will release heat. And then different freezing and melting points can be changed depending on the chemical formula. And then a really common one to look at is adding salt to things. So adding salt to roads, for instance, to melt ice, or it's a common thing in making ice cream. And the lab gives directions on how to make ice cream if you're interested. Don't have to, but in the name of science if you want to. So the first part of this lab is looking at freezing point experiments. And we have two different mixtures for you. Mixture 1 is a cup of water and ice. Mixture 2 is salt water and ice. And we already give all of the data for you, so you don't need to do the experiment. It's all here. And so we let an hour go by, and every 5 minutes took a temperature reading. So we just kind of let it melt over time, and we're seeing how just the water and ice compares to that of water, salt, and ice. And then I know the salt one goes to 65 minutes. That's okay. Extra data is okay. And the first part of this lab is going to have you graphing these. Yep, so we have the data, and then we have two different graphs for you, and then they're on Canvas. I'm going to show you how to do it in Excel real quick because it's not too bad. But if you hate Excel, you can do it by hand or any program you've been doing already. And yeah, they're on Canvas. And then you can upload them here. But for Excel, let me show you how to do it again. So I have the correct data here, but I'm going to use just an example of incorrect data just to show you the process. All you have to do is highlight your two rows. You would go to Insert, and then go to where these little dots are, where it says Insert Scatter. And I like the one with the curved, smooth line with the markers. And you're pretty much already done at this point. Just clean it up, make sure the title's correct. And then don't forget to add axes, because it's bad science if you don't add axes. And you can do that by clicking your chart, making sure the whole thing's highlighted. And then my Zoom is blocking me, but under chart design, you can pick add chart element, and you can add some axes titles here. And there you go, nice and simple. And then there'll just be a few questions asking like when just looking at these graphs, how quickly they melted, how they compare to each other, stuff like that. Nothing too terrible, hopefully. Yep. And then there'll be a question about some stuff I mentioned before. How's this comparing to the Earth? So the next part of this lab is going to be trying to calculate viscosities. So viscosity is a weird word for how something flows, and it's a really important element when looking at different lavas. So something with a high viscosity is going to be really stiff and does not flow very much. So you could think of like honey. If you were to hold honey upside down, it would flow a little bit, but not too much. And then something with low viscosity is really runny and flows quickly. So opposite of like honey, like water would flow really fast. And then temperature will impact viscosity. So if we were to heat, say, like honey up, or I'll start with cold. Yeah, I'll start with cold temperatures. If we were to freeze honey, that would increase its viscosity because the honey would flow really slowly. But if we were to heat honey up, that would decrease the viscosity because now it could flow really quickly. So because there's this heat element to it, this is really important when looking at lavas, whether we're looking at a hot lava or a cold lava. And I know it's a little weird to think of lava as cold, but it can be cold when comparing it to other types of lavas. So this lab, we're going to be calculating different viscosities of different lavas. And our lavas are room temperature corn syrup, cold corn syrup, hot corn syrup, and corn syrup mixed with sand. So We're trying to see how they compare, which one runs quicker than the other, and so on. So we have different videos for you, which are on that Google Sheets. And we're calculating how quickly they flow down this like tube. It's going from the start line to the end line. So the easiest way to do this is let the video play and pause the video when the corn syrup hits that line. So looks like it hits it around 13 seconds. So I'd make a note that the start time was 13 seconds there and let it play. And then I would cheat because some of these are going to take a few minutes. And then pause it when it hits that end line, see where that hits. So it looks like it hit that around 50 seconds. So you could just take the difference between that start and end, 50 minus 13 seconds. It took 37 seconds for this corn syrup to go from the start line to the end line. And then it's going to be easiest if you convert all of your time to seconds, which is irrelevant for this one, but some of them will take a few minutes. And then for the next part, we're going to need everything in seconds. So if you just want to convert everything now, that'll save you a step. So once you find all of your times, we can calculate velocities from it. So velocity is how long it takes something to go a certain distance within a certain period of time. So in this case, from that start to that end line, that was 30 centimeters. So then, and then we already calculated how many seconds it took it to go that 30 centimeters. So you would just have to take that 30 centimeters divided by your time. So for instance, looking at the past example, 30 centimeters divided by that 37 seconds would be 0.81 centimeters per second. That would be the velocity. And then yep, just also make sure to convert all minutes to seconds. This equation won't work with minutes in this case for the next part that we're doing. So then after we find all of the velocities, we can plug that velocity in to find viscosity. So viscosity being how quickly something flows. And we're using something called Jeffrey's equation for it, which is this kind of scary equation, but we have it already simplified down for you in the nice number forms here. And all you have to do is plug in the velocities you already found within the centimeters per second. So just as is. And it will give you viscosity within a unit called poise. And then let me see what the book lab says. So, yep. And then I'll just have a few questions about which one had the highest viscosity, lowest, and so on. And then the last part of the lab is looking at real life lavas and their viscosities to kind of give you an idea of how quickly or slowly real lavas would flow. So let me go back to my PowerPoint. So we have 3 different types of lavas we gave you: hot basalt, cool basalt, and really crystal rich dacite lava. And so we already have their viscosities, 75, 750, and is that a billion? And all you have to do to find the time is to multiply each of these by 0.58, which I just think it's kind of cool because, I don't know, we think of lava as going really, really fast, but if you multiply this by, say, 1 billion, you're going to find it actually can go pretty slowly. So just kind of a cool example. Not too bad. But yep, that is it for the lab. Just double check. Yep, and then the last question is just going to have you convert what you found for question 29 into days. And you can just do that by dividing the number you found by 86,400. And yeah, that's it. So let me know if you have any questions, and definitely enjoy this ice cream ice cream part if you have the ingredients for it, but don't need to.